Hi, and thanks for joining me for another video in the series in which I've been building experiments from the third edition of Charles Platt's book, Make Electronics. And in this video, the book introduces us to these things. And this integrated circuit here is something called a microcontroller. And this thing that it's mounted on is a microcontroller development board. And this particular example is from the Arduino family of development boards. Now, microcontrollers allow us to create devices with complex behaviors without necessarily having a complex circuit. And later in this video, I'll be showing you how this is achieved using a combination of programming and by attaching external components to this development board. But before we get into that, it's worth looking at exactly what a microcontroller is and why we might need one. The best way I can think of to set the scene for you is to start by considering something you might be more familiar with: microprocessors. Let's look at the features of a typical microprocessor. As an example, we'll use the 10th generation Intel Core i5 found in many PCs. Let's think about the typical use of a PC. Maybe during the day you'll use it for work, and perhaps you're running several applications simultaneously. And of course, to be able to do all of these things at the same time requires an operating system, such as Microsoft Windows. Now, running all these applications requires a powerful microprocessor. To achieve that, the i5 has 6 cores. You can think of each of these as being a separate processing unit that can run different processes in parallel. And each of these cores can operate at speeds between 2.9 and 4.3 gigahertz. But this power comes at a cost. It requires a lot of energy, around 65 watts for this particular chip. And that level of power consumption in a small device generates a lot of heat, which is why modern microprocessors are fitted with hefty heat sinks. There's also a monetary cost. An Intel i5 retails for around $200. And despite having all that power, the microprocessor is useless on its own. It needs to be connected to a lot of external hardware to create a functional computer. So all of this is well and good if we want a general purpose computing system. But let's say we want to embed a little bit of computing power in another device. Let's take a traffic light controller at a road intersection as an example. Could we use a microprocessor for this purpose? Sure. We'd need to create a custom interface so it could work with the connected hardware. Things like relays to switch the lights on and off, and buttons that pedestrians use to indicate they want to cross the road. But what we'd end up with is a system that's expensive to build and install, that is expensive to run with lots of extra hardware that could go wrong, and one that is frankly ridiculously overpowered for the job it's doing. Microcontrollers were designed to address exactly this problem. Let's look at how they differ from microprocessors. As an example, we'll use the Atmel ATmega328 microcontroller, which is used in many Arduino boards. One of the biggest differences is power. The ATmega328 has a single core that can run at clock speeds of up to 20 megahertz. A tiny fraction of the i5's top speed. But the point is, that level of power is sufficient for running a single application like a traffic light controller. And the advantage of this lower power is that the energy consumption is much lower too, maxing out at about 100 milliwatts. And that means we don't need to add cooling systems like heat sinks and fans, all of which adds up to much lower running costs. And while we're talking about cost, the ATmega328 retails at less than $2 per unit, 1/100th of the cost of the i5. Secondly, Microcontrollers have onboard permanent storage and volatile memory, so there's no need for additional external integrated circuits to fulfill this function. The ATmega 328, for example, has 32 kilobytes of flash memory for permanent storage, plus 1 kilobyte for data that needs to persist, like configuration settings. And it has 2 kilobytes of RAM. Now you might be thinking that this is nothing compared to the 1 terabyte SSD and 16 gigabytes of RAM on your home PC. But remember, in our example, we need to store just a single program to control the lights and very little data. For example, the current state of each light at the junction and whether the pedestrian button has been triggered. The final big difference I want to draw your attention to is how the microcontroller is designed to interface with other devices. Microprocessors use something called a bus architecture. They have multiple input-output pins that connect to 3 buses for addresses, data, and control signals. If you want to control things like relays for lights and to read button presses, you'll need an interface to these devices that is also designed to work with that bus architecture. Now that's not the case with microcontrollers. Instead of buses, they use general purpose input-output pins, GPIOs. These are designed to connect directly to external hardware. For example, they can be connected directly to the push button used by pedestrians, and they can provide a control signal to a relay for the lights. This significantly reduces the complexity of the external circuitry required. In fact, anywhere where a little bit of computing power needs to be embedded into a specialized device, more often than not you'll find a microcontroller. I guarantee there are several around you right now. In your kitchen appliances, your TV remote, your game controllers, your car. You probably have more microcontrollers in your home than microprocessors. So hopefully that gives you an idea of the benefits of microcontrollers over microprocessors for this type of application. But why do we need a development board? Well, strictly speaking, we don't. You can add the microcontroller directly to your circuit. And indeed, in many of the cases I just mentioned, that's exactly how the microcontroller is used. But what if you're a hobbyist who just wants to experiment with microcontrollers? Or even a product developer who wants to quickly prototype a new application? Setting up a development system can be tricky. You need to add a means of supplying power at the right voltage and a way of programming the device. You'll also need to add some external circuitry to provide a clock input to control the microcontroller's speed. The development board provides all these functions, as well as exposing the GPIO pins as a header to allow you to easily attach external hardware. There are lots of different microcontrollers available today, and also many different development boards. Even within the Arduino family, you have a choice. This one is the classic Arduino Uno R3. This board comes with a socketed microcontroller in a DIP package. The advantage of this is that you can easily replace the microcontroller. This isn't the case with some boards, such as this Leonardo, which has a surface mount or SMD microcontroller. Both of these boards expose the microcontroller pins in these headers along the edge of the board. As well as making it easy to connect external hardware, these also allow the use of shields. These are expansion boards that provide additional functionality and plug into the main board using the headers. A good example is this touchscreen LCD display shield. You can see this has pins on the underside that are designed to slide directly into the headers on the Uno. A recent trend in microcontroller development boards is for small form factor boards like this Arduino Nano Every. As you can see, these also have an SMD microcontroller. But the header pins in this case are designed to fit in a standard breadboard so that you can connect external circuitry that way. Okay, that's quite enough theory. Let's make this microcontroller do something. Now, one thing you won't find on the Arduino Uno development board is an HDMI connection for an external display. There is a USB Type B connector, but you won't be plugging a keyboard into this. Instead, you'll use it to connect the development board to your PC. This achieves two things. One, it supplies power to the board via the USB interface, and two, it enables a serial link between the PC and the board so that we can use the PC to program the microcontroller. Arduino provides an integrated development environment, or IDE, for creating programs and uploading them to the microcontroller. Now, the book suggests using the installable IDE, but here I'm going to be using the cloud version. Arduino uses a simplified version of the language C++. One thing you'll notice is that Arduino refers to your programs as sketches. That's because your sketch is not actually a complete program. The Arduino development environment adds a lot of stuff behind the scenes though to turn it into a complete program. So here I've opened a new sketch in the cloud editor, and you can see it's identified the development board I have connected, the Arduino Uno, and it's given me a basic template. This thing at the top is actually a comment. Comments are like notes in your sketch. Anything inside them will be ignored when the final code is created and downloaded, but they can be useful for reminding you what your sketch does. Here I'll just put this as my first Arduino sketch. For this initial sketch, we're going to start small and light an LED connected to one of the microcontroller's GPIO pins. Usefully, the Uno has a built-in LED that is permanently connected to GPIO pin 13. These next two things are functions. We can define as many functions as we need, but these two are always required in an Arduino sketch. The first one, setup, will be run just once when the microcontroller is powered up or reset. So, as the name implies, it's where we should do any initial setup tasks that are required. Now, with GPIO pins, before we use them, we need to tell the microcontroller whether we are going to use them for input or output. We do this by calling another function called pin mode. Now, you'll notice that these functions have parentheses after the function name. This is where we put any arguments that we're passing to the function. The setup and loop functions take no arguments, but pin mode does. The first of these is the number of the GPIO pin we're setting up. We could just put 13 here, but another thing the development environment does for us is define lots of useful values. We're going to use one here called LED_built-in. This is much more meaningful than just seeing a number 13. If you're passing more than one argument to a function, they need to be separated by a comma. For the second argument, we're going to use another one of those defined values, output, to tell the microcontroller that we want the pin to be an output pin. Finally, all C++ statements need to end with a semicolon. Note that what we've just done here is create a function call. We're calling a function that has already been created for us in the development environment. Whereas with setup and loop, we're creating function definitions. That is, we're writing the code that will be executed when those functions are called. Now we can move on to the second required function, loop. As the name implies, any code in this function will be run forever as an infinite loop, or at least it will until the microcontroller is powered down or reset. Here's where we put the commands to make the microcontroller do useful things. In this case, we want to turn the built-in LED on. We can do that by setting the GPIO pin to a high state. And for that, we call another function that is provided for us, digital write. This also takes two arguments. The first is the pin that we want to write to, in this case LED underscore built-in, which you'll remember translates to pin 13. The second argument is whether we want the pin to be set to a low or high state. In this case, we want to set it high in order to turn the LED on. Okay, now we have our first simple sketch. We could upload it to the microcontroller at this point. However, if you've just written a new sketch, it's a good idea to verify it first. We can do that using this button. What this does is try to compile our sketch. That's the process of turning this high-level C++ program into a low-level AVR machine code that the microcontroller understands. If it encounters any errors during the compilation process, it will show them in this console area. In this case though, everything is compiled correctly, so we're good to upload the code using the upload button. Now this will recompile the code, but it will also upload it into the microcontroller via the USB interface on the Uno. The Uno has two other LEDs that show when the USB interface is receiving or transmitting data. If you watch carefully, you'll see those flashing during the upload process. At the end of the upload process, the microcontroller will be reset and your sketch will start running. In this case, we can see that it's running because the built-in LED, marked L, is now lit. Okay, so that's satisfying to see your first sketch working, but it's a very long-winded way to simply light an LED. So let's try to make it do something a bit more interesting. Let's make the LED flash. Now what we can't do is simply add a command to turn the LED off again. That's because these commands are executed so quickly that we wouldn't be able to see the LED transitioning between its off and on states. So we need to slow things down by introducing a delay. Fortunately, there's another function called delay that we can use to do that. It takes just one argument, which is the number of milliseconds it should wait. So if we want the LED to stay on for 1 second, we should enter 1000 here. Now we can add a command to turn the LED off. This time setting the pin to a low state. And finally we need another delay. But let's make this one half a second. That's 500 milliseconds. Now, I could verify again at this point, but I'm pretty confident this sketch is correct, so I'm just going to upload it to the microcontroller. And now you can see that the LED is indeed flashing. Okay, but what if we want the Uno to control external hardware? How can we do the same thing with a normal through-hole LED? Well, let's set that up. You can see here I've got a breadboard with an LED. Don't forget to include a current limiting resistor. You'll need it here to protect the LED just as you do with an analog circuit. You can see that the header is labelled to show which pins it is connected to. And I've connected a wire from GPIO pin 12 to the anode of the LED. The cathode of the LED is connected to the current limiting resistor, which in turn is connected via a wire to a ground pin on the microcontroller to complete the circuit. Now we need to make a couple of changes to the sketch to tell it we're using a different GPIO pin, pin 12. That's done. So now I can upload the sketch again. And there you have it, one flashing LED. Well, I hope you found that a useful introduction to microcontrollers. But I am aware you may be feeling a little underwhelmed by what we've managed to achieve in this video. In fact, you may well recall that way back at the start of this series, we were lighting an LED using nothing more than a battery and a resistor. So you may well be thinking, well, what's the big deal with these microcontroller things then? But of course, with something this complex, we need to start small and build up from there. And don't worry, because we have barely begun to scratch the surface in terms of the capabilities of microcontrollers. In fact, in the next video, the book shows us how to recreate an earlier experiment, the electronic dice, but this time using a microcontroller instead of discrete logic chips. So if you're interested to start to see some of the true potential of microcontrollers, please do join me for that. See you then.